Today I'm going to be presenting on the developer experience gap, which is actually an article written by O'Grady at RedMonk about 1.5 years ago. And I'm going to be talking about that within the context of the Kubernetes ecosystem. So first, a quick introduction. My name is Mark Fisher. I'm a tech lead as part of VMware Tanzu, where I work on our developer and application platforms. So that includes Tanzu Application Service, Tanzu Application Platform, and a lot of open source that supports all of that. And today I'm going to be focused on mostly those open source projects under the covers. I spent more than a decade on the Spring team. I've presented at Devnexus 7 different years, so a number of topics ranging from Spring integration, Spring AMQP, Spring Batch, and Spring Cloud Stream. And then about 5 years ago, I kind of switched off of the Spring team and started focusing on Kubernetes-based developer platforms. And we started something called Riff, which was a function as a service platform that was kind of focused on stream processing. And that project is no longer active itself, but some of the pieces live on in other things, like we converged that team with the Knative team at VMware. And so some of the work around functions via build packs is living on through Knative. And like I said, now I'm on the VMware Tanzu team. I'm going to be walking through a lot of these projects here after we talk a little bit about the developer experience gap article. So you're probably not going to learn the in-depth detail of any one of these because I'm going to be moving very quickly. What I want to focus on is each one addresses a certain domain, exposes APIs, and that there's a consistency to the way all of these are extending the Kubernetes ecosystem. Okay, so this slide, who's seen this before? Probably it shows up in a lot of presentations, the CNCF landscape. And the fact that you probably can't actually make out any of those icons from where you're sitting is kind of the whole point. Like, there's so much out there. And in the Stephen O'Grady article, he refers to this as the embarrassment of riches for developers today. And in addition, there are hundreds of public cloud services across AWS, Azure, and Google, for databases and streaming platforms and compute engines and all kinds of things. So this article, I highly recommend reading it. You'll notice here in a moment that I had a hard time finding just a couple quotes to include, so I've included a lot. But the main point here is, like we saw on that slide and all these public services, there's everything a developer could possibly want, but the challenge becomes how you put all those pieces together. And what ends up happening in a lot of organizations is that you create this patchwork quilt of products and services, and the application team ends up maintaining that. And ultimately, it takes away time from their actual application development because they're spending so much time on tool chains and infrastructure. But this is somewhat necessary because monolithic solutions don't really fit the world today, where applications don't have a one-size-fits-all model, right? Like, we're not really building nearly as many 3-tier applications as we used to. There's streaming applications, there's mobile, back-end for front-end applications, there's all kinds of different microservice patterns. So this diversity is actually a good thing. But this is what he refers to as the developer experience gap, right? On one hand, having all of this available, but then having to put the pieces together, and that takes a lot of time and effort. And then looking forward, he describes what he thinks the focus should be, that solutions need to be comprehensive. So the more that there are consistent APIs, things can be plugged together like Lego blocks. That part can be much more efficient. Also, developers need tools that meet them where they are, right? Like, so this is why GitOps is a very popular, one reason that GitOps is popular right now, because developers are used to working with Git. So the more that they can have automation driven from something that they push to Git, then that allows the developer to kind of stay in their flow. And so that user experience for developers is really important. And also, he points out that pretty much any solution these days needs to be multi-runtime, right? Polyglot from a developer's perspective, and that no vendor can provide all of the tools that every developer is going to need. So within a large organization, you might end up with an opinionated platform, but that opinionated platform is going to be customized in some way for that organization. And the question is whether the development team is the one building that platform instead of creating their applications. So the more this can be, the easier this process can be, the better it is for developers. Okay, so now let's look at Kubernetes. Just going to scratch the surface here a little bit. But I wanted to point out how Kubernetes is described in its own documentation. So of course, I think everyone knows that Kubernetes is a containerized workload orchestrator and provides abstractions for infrastructure services like storage and networking. And it's great for platform operators that need to have a portable abstraction layer across different IaaS, different public clouds, private clouds, and so on. So Kubernetes is a great abstraction for platform operators. It's also, I think, what I've bolded here is the part that I want to focus on more today, is the fact that at the core, what's really powerful about Kubernetes is the reconciliation engine and the API that it exposes and that it makes extensible. And that's why there's such a growing ecosystem of projects built on Kubernetes. But what they define that Kubernetes is not is actually even more telling. It's not a PaaS. It's not a full end-to-end solution for development teams. It's really providing building blocks to build developer platforms. So it's a great abstraction for platform operators. It's not a great abstraction for developers. But it provides all the tools to create great abstractions for developers. And so that's what I want to focus on today. Now, despite being described as not a platform for developers, they do have a developer certification for Kubernetes, which is interesting. But if you look at the curriculum, it's all very low level, right? Building and modifying containers, dealing with network policy, applying configuration and secrets for credentials that you need your applications to be able to connect to, and all of these types of things, deployments and rollouts. It's a lot of platformy type things that support applications, right? And this stuff is very relevant to anyone who is extending Kubernetes and needs to be a developer on Kubernetes. But we're luckily seeing more and more projects building on top of this so that developers don't have to think about all of these details just to get their application running on Kubernetes. Okay, so I'm going to focus on a very simple example, just a Hello World app, basically, and what it takes for a developer to get that deployed onto Kubernetes at this low level. Of course, a developer needs to write their code. They need to test their code. In order to get it onto Kubernetes, they need to build an image. And then they need to reference that image from the configuration that they apply to the cluster. And then that's how it gets deployed. So there's a lot of steps here. Ultimately, the developer should be able to focus on writing their code and also writing their test code. But the more that boilerplate of all the configuration can be handled for them, the more productive they'll be, the more they'll be able to remain focused on their application. Again, this is a very simple example. Just hello world, and it's pointing, you can see down in the container part of the specification, it's pointing to an application image. There's a deployment. Deployment is going to be responsible for creating pods. Now, you could create a pod directly in Kubernetes. That's the really lowest level of unit of deployment. But the advantage of using deployment instead of pod is that you can control the number of replicas in one place. And so a common pattern that you'll see in Kubernetes extensions is these layers, right? And the deployment has a template. And you're going to see a lot of templates in Kubernetes configurations. That template is the part that would be mapped right into a pod if you were creating the pod YAML directly. You could basically copy and paste inside of that template, call it pod.yaml and apply that, and it would create a pod, right? Now on the right-hand side, there's a service. And the other thing I want to point out in addition to templates here is the use of selectors. So in Kubernetes, every object can have metadata, and within that metadata it can include labels. So it's a really common pattern to have this loose coupling of associating objects, referencing them by those label selectors. So you can see that the service has a selector on a key value pair. In this case, it's really just the key that matches a label that will be in those pods that get created by the deployment. So there's kind of a lot here considering that's all that it does, and the things I list here that aren't included that you would have in a typical real-world app, like configuration and secrets that need to be mounted into volumes, setting the CPU and resource requirements, adding probes for your liveness and readiness checks. All of those things are important as well. And then, not even getting into exposing this as an ingress via an ingress for public access, or connecting to other data services and other APIs. Okay, so what is powerful about this model, though, is that the deployment is basically the owner of these layers. So a deployment stamps out a replica set. Replica set is told, in this case, I need to create 3 pods, and it has the template. So now we have 3 pods. And that means that there's this continuous reconciliation loop behind the scenes, and if I delete a pod, a new one will be created because the replica set has that template, and it's always watching to make sure that there's 3. So it's self-healing in that sense, right? And you can easily shut down applications and have them restart. Another thing that you can do is create a new replica set. You can basically do a rollout at the deployment level, and that will create a second replica set and spin up pods. So let's say you update an image, and now you want to do a rollout. So you use a rollout command at the deployment level, and it creates a second replica set, and it can delete pods from the first replica set as it adds them back to the second replica set. And you end up with a rollout across those. This kind of rollout is only at the level of granularity of the number of pods that you have, right? So you'd have 33% basically is as fine-grained as you can get. In a little while, we're going to talk about another way to do an actual canary rollout where it can be percentage based on the actual routing traffic. Now, if I delete the deployment, the other thing here is the deployment, since it's the owner of the replica set and everything underneath it, then that will delete that cascade. The cascade will delete. The delete will cascade to those resources, right? So I only have to delete that one thing, and everything else goes away. So that's another useful aspect of this when you have the layers. Now, like I said earlier, the powerful part of Kubernetes is that it is this continuous reconciliation engine, and it's extensible. So early in, this was not an original design within Kubernetes. They had their resources, and then there was an idea to expose what they originally called third-party resources, so that users could bring their own definitions and add them to the API. And those later became named custom resources, and you can define something called a custom resource definition that represents new types that you want to be able to manage in the API. And so this is what allows this entire ecosystem to develop. So this is a simple example. I've got widget as a example type. The important thing here is that there's a spec and there's a status. And so it's almost like this is your request, this is your response, but it's a continuous thing. So you can watch that status and see what's happening with this actual resource. And you write to the spec and you watch the status, basically. And you immediately get this, it's an extensible API. You have now your resource added to the Kubernetes API. If you talk to the API server, which is, kube control is basically just like a wrapper around curl for the API server with the domain model exposed. So now you can get your widget from kube control. You don't have to add anything to kube control to extend that, as long as you've created your own service. So this is the part I think developers should understand about Kubernetes, is just this data model. Like there's a kind, there's metadata, there's a spec, there's a status, and everything that extends Kubernetes is going to look this way. And even if you're building on higher level abstractions and you don't have to write deployments and pods and think about all the details, you're always going to see this model exposed. And if you are a platform extender, you're actually developing on top of Kubernetes, there's a lot of tools out there to make this job easier. And you definitely don't want to build it all completely from scratch, because there's a lot that you can get wrong. This is just an example from controller runtime. And there's a project called Kube Builder that allows you to easily kind of template out controller runtime based reconcilers. And this is if you're in the Golang ecosystem. And what you see here is there's this manager there's one manager within the process, but you can have multiple controllers if you're watching multiple resources, and they can share the client that connects to the API server, and they can share a cache. And so that's much more efficient. Anytime resources are being updated, then you essentially write a reconciler, which is like a callback for the events that you're interested in. So if I want to watch every time my status on a widget changes, I would just write a widget reconciler, and it would hand me the widgets every time they change. And I might create another resource that's a child of that, or I might update something else in the status, or you can basically do anything you want to in that code. There's also webhook support, so you can do things like set defaults and do validation there. So these are the extension points of Kubernetes. Okay, so now what I'm going to do is I'm going to walk through several different projects that create custom resources and expose them as part of the API, and we'll talk about what each one does, kind of the domain that they focus on. Okay, so starting with Carvel. Carvel began as a set of tools that was called K14s, which was supposed to be a shortened form of Kubernetes tools, and it was a set of command line tools. I'm not going to talk about every one of them here, but I'll just focus on CAP, because that's really kind of the core of it. What CAP does is it's like a wrapper for kube control that does a diff. So you can have a set of configuration that you want to apply, and when you apply it, and when you make changes and apply it a second time, it will show you what's going to change and ask whether or not you want to confirm that change. It also keeps track every time you do make a change by storing that information in a config map on the cluster. Right, so it's not storing anything client side, it's putting it on the cluster, and you can access that and basically see what happened. It allows you to manage the set of resources at a higher level, right? So you want to think about things like that deployment and that service. I mentioned you can delete the deployment, and it'll delete the replica set in the pod, but it wouldn't delete the service, and the service would still be hanging around with nothing matching its selector. So with CAP, you can create this unit of an app and manage those together. YTT is another interesting one, which is basically a templating model that understands the structure of YAML. So it's not just text-based templating. You can work with things like maps and lists, and it understands those. And it can do templating as well as overlays so that you can basically patch existing YAML. Now, those are command line tools, but Carvel does introduce these custom resource types that extend the Kubernetes API as well. And we're going to walk through these different layers so you can see what they're doing. First, we have the app custom resource. So this is basically just a custom resource representation of what I was describing around CAP. But you can see here that there's this fetch section. And in this case, we're using Git, but it's a pluggable strategy. So you can fetch, you could put inline resources here if you wanted to. You can refer to a config map that includes those resources if you're doing that in a development environment and you don't want to bother setting up a Git repo. But if you do have a Git repo, this is like the entry point to GitOps, right? This GitHub URL here is pointing to the same sample application that I showed you earlier with the deployment and the service. But now that means as a developer, I can just make changes to that app in the configuration, push it to Git, and it's going to be updated on the cluster as long as I've registered this there. And so when I use kube control, I can get the app CR. I can also use the CAP CLI to inspect and see the list of everything that's included within that app. So you see the deployment and the replica set in the pod, also the service, and the service has sub-resources as well that I didn't show in the slide earlier, but endpoints and endpoint slices. So all of this is being handled as a unit. Okay, the next level is the package, and in order to manage packages, there's something called a package repository. Package repository is basically just a collection of package metadata. So when you register this in the cluster, there's a reconciler, and that reconciler will create packages. And so when you do kube control get package, now you see all of the stuff that's available to be installed from that repository. Nothing's actually installed yet other than these resources themselves, but now all of this is available. So in the example here, we want to add Contour so that we can add an ingress with the Contour HTTP proxy alongside our service. And so we're going to choose 117.1 of Contour, and we can look at that metadata here, right? So you can see it's metadata, and then it has a template, just like we saw earlier, but this template is templating a CAP controller app CR. So it can fetch from either a Git repository, or in this case, it's fetching an image package bundle. So that's an immutable digested image that includes this configuration, which is a nice way to be able to share packages, right? So you're guaranteed to always get the same content if you're using that digest. So once you have that, you can create a package install. There's also a CLI for this, so you don't have to create all this YAML. And the package install is actually an instruction to its reconciler to install whatever's in that package and basically use cap under the covers to apply those resources and manage them. And so now we see that we have a package install for Contour, and then this one also shows Cert Manager has been installed. And now I can create the HTTP proxy, which is a Contour custom resource, because Contour's operator is going to be watching that. And if we add that to the Git repo that we were talking about earlier and push, then the underlying app CR will see that change and create the HTTP proxy so that the next time we look at do a cap inspect, we see, in addition to what was there before, we also have an HTTP proxy now. Okay, so that's a very quick overview of Carvel, just to understand these layers. There's a lot more to it. Now I'm going to talk briefly about build packs. Build packs are a way that you can create images from source without using Docker files. And there's a focus on the layers of these images, which we'll see in a moment. Now, build packs, we saw earlier in the O'Grady article, he talked about like multi-runtime is something that we need to accept. Build packs, you can set up a list of build packs, and every time you try to build source using that builder, it's going to go through the list of build packs and call a detect, which typically looks for something like a POM file if it's a Java app, and that Java build pack takes care of that. Or package.json if it's a Node app, and the Node build pack takes care of that. Sometimes multiple build packs might detect that they can contribute something based on files like Node and Yarn. Under the covers, there's a builder, and the builder basically refers to what's called a stack, which includes an image for the builder pod, or the builder container, and an image that will be the base image for the applications that get built. So the builder drives this process and can be updated independently of the applications. And the build packs, so Cloud Native Build Packs as a project is focused on the specification. And I should have mentioned that this is a CNCF incubating project. It's a collaboration between Heroku and originally Pivotal, now VMware, and Heroku's now Salesforce. But that was started around 2018, and both Heroku and Pivotal with Cloud Foundry had build pack technology going back quite a bit longer than that. But they've created this standard, updated the way build packs work at the spec level, and that's all that the Cloud Native Build Packs actually focuses on. There aren't implementations of build packs in the Cloud Native Build Packs project, but there are separate projects for, like Paketo is a project that actually includes build packs. But there are others, and vendors created their own build packs. So there's this independence between the spec and those implementations. Now, any actual platform or basically build pack spec compliant runtime can use this model and use the builder image, builds an application, use the run image as the base layer for that application, and now you have a container image. And then what's really powerful about that is that if you want to patch the underlying run image, that can be done through a rebase process. So it updates the image metadata, but it doesn't have to go through another build, right? So you only really have to rebuild if you've changed the source code for those layers that sit above for your application. Okay, so there's, again, a lot more to build packs, but that's a quick introduction to what they do. And then Kpack is the custom resource model on Kubernetes that drives build packs inside the cluster. So it spins up pods for the build, and it creates images for your application and pushes them to a registry. Okay, so these gray boxes inside the dashed line are the custom resources that are defined by Kpack. So you have that stack with the run image and the build image referenced by a builder. And then you have the store, which is the list of build packs that you want to make available here. And then image, from like a domain-driven design perspective, image is like the root entity, right? This is what you're going to interact with as a user. You'll update the referenced source for that image, and that will trigger a build, right? And so what that looks like is the build gets stamped out. So image can be updated, but builds are immutable. So a new build resource is created, and that corresponds to a new image in the container registry. But one of the important things here, and this is a common pattern you'll see with Kubernetes extensions, API extensions, is that you don't have to go look for those builds yourself, because since the image is the owner and stamps out the build, it reflects the latest build in its status. So you can interact with the image and you can watch the image to find out about the latest build, and it will give you the digest of the actual image in the container registry. So you don't actually interact with that build resource directly. So there's just a nice single interface from a user's perspective. Now, when we do a rebase, or we update the stack and patch the underlying operating system, that will also create a new build resource and a new image in the registry. But like I was saying earlier, it doesn't actually have to go through the build pack process for your source code. And so that can be very quick. Okay, now I'm going to talk a little bit about Tekton. Very briefly. So Tekton also introduces some custom resources. What's interesting here is everything we've been talking about is like continuous reconciliation of these very loosely coupled resources. But sometimes you need to do something that executes a series of steps. And that's where Tekton comes in, to allow you to do things like CI pipelines that run on your Kubernetes cluster. So a task is one custom resource, and it basically maps to a pod. And a task can have multiple steps, and those steps are mapped to containers within that pod. So you might have 3 steps, you'll have 3 containers in a pod, and because they're in a pod, they're basically co-located and can share pod-scoped storage. So one step can do what it needs to do and write a file, the next step can read that file, and so on. There's also pipelines, which add one level above that, and a pipeline can refer to multiple steps, and you can basically create a directed acyclic graph. And the task and the pipeline custom resources are like definitions of the process, but if you want to run one, you have to create another resource called task run that refers to that task, and that will execute with certain parameters and give you a status, or pipeline run, and that will create task runs for each of its tasks and record back the status. So there are these objects that get created that live for a given instance of the task or pipeline executing. Okay, and now we'll talk a little bit about Knative. Knative also introduces custom resources through the Kubernetes API. There's 2 main parts to Knative. Originally, there was actually Knative build, which spun out and became Tekton, and it's a more general purpose engine, so that really made sense. But today, Knative consists of serving and eventing. We're going to mostly focus on serving, but I'll just mention something about eventing, which is interesting. So eventing has custom resources for an event source, and it's focused on cloud events, and you can set up a trigger, and when this cloud event occurs, you can invoke something that is addressable. And so in Knative, they introduced this idea of duck typing for those resources. So an addressable resource is something that has a URL in its status, but there can be many different types that actually expose that, and any one of those can be at the end of a trigger. So it's another way to create really loosely coupled contracts. Now on the serving side, the primary characteristics that Knative adds to your Kubernetes cluster are revision management and weighted traffic routing. So what this means is that you define this one top-level thing called a service, and it creates sub-resources called configuration and route. A configuration is like the mutable thing, kind of like image was for KPAC, and every time there's a change to it, it will stamp out a revision. So if you update your code and you point to that in the configuration, it stamps out a new revision. If you update an environment variable in the configuration, it stamps out a new revision. So those revisions are immutable. And then the route can actually point to the revisions with different weighting for the traffic. And what that means is what I talked about earlier, rolling out at the deployment level, it's only the granularity of pods. Here, you can have a weighted routing at any level that you want, because this is going to drive it at the ingress that's associated with these endpoints, right? So you can have 10% of your traffic even if you only have 2 pods. Or like you can have one pod that's revision A and another pod that's revision B, and it can manage the 10% of those because it's doing it at the ingress level. Okay, it also supports auto-scaling, and it supports auto-scaling to 0, which is why Knative is described as serverless, right? Because you can completely scale down when it's idle. And the way, I'm not going to talk about every detail of this slide, but there are a couple things that are worth pointing out. One is that it's different than the HPA, horizontal pod autoscaler that is like core to Kubernetes, in the sense that you're not just watching metrics for things like CPU usage and memory usage, it's watching metrics on the request traffic itself. And it does that by adding a sidecar to each one of these applications. You see the queue proxy, and that's providing those metrics that allow it to make decisions based on traffic. And then over here on the right-hand side at the bottom, you see activator. And what happens there is when you scale to 0, it can redirect that service to point to the activator. And now the pods can scale down, and you still have an endpoint available for your application to be invoked, but there's nothing currently ready to handle those requests until you scale back up from 0. And then it basically, the activator buffers the request while the pod spins up. This is why cold start is a real concern in this model. And has anyone gone to any sessions on Java native this week? Yeah, so big topic that's definitely relevant in this world. If you can start a Java application in milliseconds, then you can really take advantage of the serverless model. And then that's much more efficient from a resource utilization perspective. Okay, let me just check where I am. I forgot to start my stopwatch. I think we're okay. Service binding. This is a relatively new specification, started as a collaboration with mostly IBM, Red Hat, and VMware. Others are starting to get interested as well. It's very simple, narrowly scoped. And what it basically does is it provides a custom resource that extends your Kubernetes API, right? You're seeing this pattern. And the service binding can reference a service and a workload that needs to have that service, the credentials and the binding properties necessary to connect. The workload needs those to be injected. And so the way that this works is that a service is a duck type. I talked about addressable being a duck type with Knative eventing. The service is also a duck type. It just needs to have a secret reference in its status. And then the deployment can have that secret reference added so that every time it stamps out a pod, there's a volume mount with those credentials injected. Okay, so this slide makes it maybe a little more clear. You can see a service binding resource is defined. Its spec has service and workload. And these are, it's a common thing you'll see in Kubernetes resources when it's an object reference. It has the API version, the kind, and the name of the thing that it's referencing. So that's a reference to another resource that would exist in this cluster. It might not exist, right? This is a continuous reconciliation model with eventual consistency. So if that service doesn't exist, then the status for this binding would show that it's pending. And then someone adds that service, then it can actually follow through and do the reconciliation and then update the status to be bound. But what it refers to on the service side is anything that matches this duck type, which has the binding name, and that's a reference to a secret. The secret can have these key value pairs that are needed for a workload to connect to that service. And this is what is really probably the most important part of the service binding spec, is defining what those key value pairs should be so that they're consistent. So every time you have a MySQL database, you would have a secret with these key value pairs in it, and then you can mix and match any MySQL, and hopefully we get to that point. Now, what this ends up doing then is it creates that volume mount for the pods that are created by this deployment and adds the keys and the secret as files, and then the contents of each file would be the value. Does that make sense overall? And if you're using Spring, how many people are using Spring? Okay, it's always a good question at this conference. There is a Spring Cloud Bindings project that is able to take those volume mounts and populate the corresponding Spring properties, like spring.datasource.url and spring.datasource.username and so on. Those properties will be, it's basically a property source, right? So instead of having to put these in application.yaml or create environment variables or other ways that you might do this, they'll automatically be bound because of that volume mount. But the workload doesn't know that Kubernetes provided that file, right? You could put that file there to yourself, define it statically, and this would still kick in and work. So there's this nice separation between those. And because this is relatively simple, it's just a mapping, all of these projects that are listed here on the right-hand side are already supported by Spring Cloud bindings. And what it's doing is it's converging on these simple names, like if there's a host, call it host. If there's a username, call it username. And we can have consistency now across all these different databases and messaging systems and so on. So those get bound automatically. Another thing, since it's mostly a Spring audience, we can think of service binding as dependency injection, right? It's literally providing this configuration, injecting it into a volume on the workload. But it's also acting kind of like a bean post processor, right? As this is being instantiated, it's updating the definition so that you don't have to have this upstream. It's not something that you're responsible for in a Git repository. It's going to be handled in the cluster right before this instance becomes a running workload. Okay, and now let's look at Flux. So just a couple slides on Flux. This is an open source project that was started by Weaveworks. It's also a CNCF incubating project. Flux version 1 was a relatively monolithic GitOps solution, and they decided with their second version to decompose that and make it usable in a modular way, which I think was a really smart move, and it's getting a lot of adoption now. So there's, on one side, you've got source controllers for things that you're reading as the source of truth and then reflecting in your cluster. And on the other side, you've got things like Customize or Helm that can actually drive deployment into the cluster. And then they also have support for things like notifications so that you can configure Slack messages to be sent when something's updated and so on. So there's a lot of pieces, and there's, I think what's particularly interesting about it is that we should really always think of GitOps in quotes because it's not necessarily Git. Like even this thing they call GitOps Toolkit has different options for the source controller. It can be reading Helm charts from a Helm registry. It can be reading configuration that's in an S3 bucket. Like they actually have an implementation that can read that instead. So the key point is not so much that it's Git, it's that the state in your Kubernetes cluster is always ephemeral, and the state in your source of truth is separate from that, right? So version control normally is the right way to go, but it could be an image in a registry, which is something that we use in VMware Tanzu. We have an image registry source, right? So you can put all of your Kubernetes YAML into an image like we saw with the image package, and you can refer to that as your source of truth. And then you can bump a new version of that, and it will see that inside your cluster. And what this looks like, this is one resource here that I chopped in half so you could see the spec on the left and the status on the right. But it's a single resource called Git repository. And in the spec, the important thing is it has the URL for the Git repo, and it has the branch. And it has an interval, which in this case is 1 minute, but that's adjustable, right? So this is going to be polling that Git repo and checking for changes. If there's a change, it's going to reflect it in the status with an updated artifact, and it provides the information about that, the revision, all of the metadata for that, as well as a URL. It actually makes it available inside your cluster on the source controller itself as an HTTP server. So other components within your cluster can watch for that. When they see the status has changed, they can grab the source code that's been pulled from Git. You can also do this with Git webhook, so you don't need that interval, and it can be invoked in a push style from Git instead. Okay, so this overlaps a little bit with what I showed earlier with Carvel, where we're doing a Git fetch directly from that resource. But in this case, it's more pluggable because you can represent this one Git repository. This could be for your source code of your application, and then we want to drive something like Kpack after that, or even a Tekton task that uses Conoco instead and builds with a Docker file. Like different things can be plugged in on the other side of this. It's very loosely coupled in that way. It also allows us to swap out those different implementations. Like I said, they have support for all the different flavors of Git. You can point to an S3 bucket. You can point to an image registry. So there's a lot of flexibility built into this. Okay, and now I'm going to talk a little bit about Cartographer, because I think at this point, it probably looks like I just added 8 more projects that you need to learn about, and now it's even more complex, and the developer has even more things to worry about. And what's interesting about Cartographer is that it takes advantage of all of these Kubernetes resources conforming to this API model and allows you to make connections between them. But otherwise, purposefully remains very, stays out of the way. Doesn't bring a lot of logic. So the basic idea is it uses templates, and up at the top here you see that an operator would typically configure the templates that are available within your Cartographer instance, and then those templates can stamp out resources. So on the bottom, the resources in red are the ones that are being stamped out by a Cartographer or updated when something upstream changes. This allows you to create this kind of cascading effect, and we refer to it kind of like pipes from a Unix pipes perspective, right? Because the status of this resource changes, I want to update the spec of this resource. Now that resource does something like kpack, builds an image, and then its status is updated whenever that's completed, and now the new latest image is shown, and I want to update something downstream from that to maybe roll out a new deployment with that image, and then that kicks off something else, and I can watch its status, and so on. So that's the way that this model works, and like I said, it is purposefully thin and doesn't get in the way. It's not really a reconciler of its own. It's just passing data from one resource to the next. And it's also doing it in a way that's not like Tecton. These are not steps in a workflow where the whole thing either completes or not. It's a continuously running system, and anything might change anywhere within that graph and cause everything else downstream from it to change. So like in the kpack case, if we rebase if we update the builder, we update the stack, we patch a run image, that will also change the kpack image, even if the Git repository upstream from that didn't change because you haven't changed any source code. Everything else downstream, if it's being managed by Cartographer, will still roll out a new application because it's just watching one thing upstream from it. So one of the things that we use this for is to create supply chains. And a supply chain basically takes a workload as its input. And workload is intending to be the YAML that reflects what a developer actually cares about, right? So we have the location of the source code. You can set environment variables here. The other thing this has is a service claim. So service claim petsDB, right? This is the Pets Clinic example, and it has a ref with API version, kind, and name like we saw earlier. So this is an object reference to a database type. It would be anything that implements that duck type that service bindings work with. And so that service claim is the developer saying, I'm going to need one of these. This is like a bean definition saying it needs an interface to be passed in, but you don't care about the implementation. That's going to depend on the environment where this lands. Okay, so that's the workload going into a supply chain. And then you probably can't read it, but this one in particular, and it's very flexible, you can do anything you want, but this one is going from Git repository that would be created with this Git URL as it's in its spec, creates a kpack image. When that's updated, it's writing to a config map, and then there's a Git writer that takes that content of the config map and writes it to a Git repo. Then we have delivery of the application. So the difference here is it also points to a URL in a Git repo, but this URL represents all the Kubernetes YAML that needs to be applied for the app. So it's typically a different repository than where the source code lives. And this decoupling of supply chain and delivery is convenient because they might run on the same cluster, but you can see right here where this GitOps repo is in the middle, we could draw a line between these and we could have a separate build cluster from a runtime cluster, which is definitely a common practice when you're at a certain scale, right? You might not do that on your development cluster, but when you get into all of the concerns around a secure supply chain, you want to treat your build cluster and access to that build cluster separately from the runtime cluster where your workloads are accessible. And that's where GitOps also becomes increasingly important. You probably don't even want your developers to be able to use kube control and create resources directly on the cluster. You want them to write to Git repos, and only the cluster talks to the Git repos. All right, got just a few minutes. I have one quick demo, so I want to make sure I get to that. This is just showing how Cartographer, I said, it's not itself a workflow engine. It's not running sequential steps that have to be run together, but it can delegate to something that does that. So earlier when I was talking about Tecton, you can create a task run or a pipeline run, but then you have to watch that thing for the status. What Cartographer does is it provides this runnable abstraction that can stamp out those things and report back their status. So now you have a single thing that would be like, here's the latest pipeline that ran. And then watching that, you can update something else downstream. So we can insert this in between the Git repository and the KPAC image and run CI tests on that code using Tecton. You could also use Tecton to build instead of using KPAC, right? And this is where we want to be able to support integration of whatever tools the developer chooses to use. All right, and then this is the last topic here before I show a quick demo, and I won't show you any more projects after this, I promise. But this part in Cartographer is called conventions. And what this does is essentially enrich the pod template. So we can keep things really simple in terms of what is upstream in a Git repository, what a developer provides. And a convention can be, it's like an extension point that you might bring your own opinions for your organization into this. Or you might mix and match your conventions with some that are building in the community, which is something, we're just trying to get this started. But at the bottom, you can see a convention today can be implemented as a webhook, but we also want to be able to add support for just, in the case where YTT is enough, like you can apply an overlay to a pod template, then that should also be an extension point. You don't need a running web server for that. And then we're also starting to look at WebAssembly as an extension point for this, because it's a really good example where all that's happening is a pod template comes in and an enriched pod template comes out. So it's essentially a function that you need to invoke. And to make this a little more concrete, and you probably can't read the slide, but these are the components that are involved. So pod intent at the top, all that includes is the workload container and its image. So this comes out of, this could be the result after, say, using KPAC. Now you have an image, but KPAC images also include an SBOM. And that's the part that you can drive the conventions from. So a convention can look at this SBOM and decide what else needs to be added. And in this case, what we're showing, I'll zoom in a little bit, still probably can't read it, but on the left, it's just the pod intent. It's really just the container name and image. And on the right-hand side, there's a spec. So this is reflected in the status of the pod intent. So that's like the unenriched spec is now enriched in its own status. And it shows liveness probes and readiness probes being added because it has Spring Boot 256 actuator in the SBOM. So it knows it can add the Spring Boot liveness probe and the Spring Boot readiness probe, which you want to have when you're deploying this to Kubernetes, but you don't have to put those liveness probes and readiness probes in 100 different Git repositories upstream because you can apply it here in the cluster. And if you update that boot version and the liveness probe changes its location, which it did sometime last year, this would automatically handle that instead of having to update all of those upstream repos. So you can enforce more consistency here. It's essentially, like I was saying earlier, the Spring service bindings was like a Bean postprocessor. This is like a Bean factory postprocessor, right? Like we're updating the definition before we actually apply it to the cluster. So there's an analogy there. Okay, so once we put all these pieces together, we get to, like if you remember back on the earlier slide, the developer had to code, test, create the configuration, apply the configuration, and all of that. Now, all the developer really has to think about is their code and pushing it to Git, right? So we meet the developer where they are. They focus on Git. At the point that they created this application the first time, they would have registered that workload with the cluster, but that's a one-time thing, and now the cluster has the continuous reconciliation of updates to that Git repository. And now we get to see if it actually works, and it probably depends on my network connection, because I'm using GKE, and we'll see how this goes. So what I'm doing here is I'm just going to print out kube control git all, which is a category, so that it's not literally everything that's in Kubernetes, but it'll provide all the core Kubernetes resources. KPAC, so we'll see some of those resources for KPAC, and then Knative. And at the moment, all we have is the service for Kubernetes, right, which is the API server itself. And we have the machinery for KPAC that's already been installed. The cluster stack, the cluster builder, cluster store. So that's the build packs, the build and run image, and the actual builder. But there are no runtime instances here yet. Now, what I want to do is I'll show you this, this workload. It's a very simple example. It's just pointing to a Hello World app with a Git URL and a service account. And one thing I didn't mention earlier is that the workload has a label. And it's actually the supply chain selecting the workload, not the other way around. And this is another example where it's Spring-like. It's inversion of control. It's the Hollywood principle, right? Supply chain, a certain supply chain knows that it's responsible for web workloads. Another supply chain might be responsible for tasks. And they'll watch based on those types. But a developer doesn't say, I'm going to use this supply chain or that supply chain. They just label their application. All right, now when I apply this, what we should see happen, on the left-hand side is it's going to spin up a workload resource first, right? There we go. And then we'll see the build. And I've got KPAC CLI here, so I can say build logs demo. And we can watch the build happen. Over here, we see this pod. And build packs run in init containers, which are run in order. And so there's 6 steps that need to run to do the detect and the build and the export of the image. And here it's logging, so we can see those steps: analyze, restore, build, and then eventually it will do an export. Once that happens, we'll see the Knative resources over here, because there's a template in Cartographer that stamps out a Knative service. And then we'll have a route, and then we'll have our running workload. And this would happen if I go make a change to this app and do a git push. This would happen again, right? And then it'll roll out a revision in Knative. Okay, there goes the export. So it's pushing to Docker Hub, and that's complete. So over here we should see the Knative. Okay, so here's Knative revision, Knative service, and it's got this URL here for that app, and I can curl. Let me see. Hello World, there's the app. And again, we can delete just this demo workload, and this is also nice because everything cascades from that one workload, right? All of the resources go away except for the ones that were there when I first brought this up. So the pod is terminating, but all of the KPAC related build stuff, all of the Knative stuff is gone now. And so that's all done that way. And then I've just got one last slide here, which is Tanzu Community Edition. This is an open source distribution of VMware Tanzu. And you can see here on the right-hand side, everything that I talked about except for Tekton, which I think will be there soon, is available as Carvel packages so that you can add a package repository, like I showed earlier, and then just install Cartographer, install Knative, install everything that I showed today, or just the parts that you want to use. And then there's several other things here as well. Okay, so I think just about barely over time, but I know that there's a break right now, so I can take questions if anyone wants to come up here. But otherwise, all of this is in GitHub. Every one of these projects has a Slack channel, either on CNCF or Kubernetes or its own Slack, and that's all available here if you want to dig into any of these on a deeper level. Okay, thank you.